Yes. Okay, so let me start with thank the organizer. I don't know if it works. Yes. Thank the organizer for giving me the possibility to speak here. It's a pleasure, always. And also the funding agency for the support. So I will make a step backward. I will go back to the electromagnetic case, but again, I will speak about non-equilibrium. And in particular, I will speak about quantum friction. I'll tell you in a moment. And what quantum friction is, probably some of you know about that. And I will focus on the statistical aspects of quantum friction. And I will put the accent on two features, which I believe are quite, there are quite recent results, but I believe that those features were not treated before in this field. So let's go to the point. What is quantum friction? So I give you a very intuitive picture of it. So it's a kind of dynamical version of the cosmic force. So you know, if you have an atom in front of a surface, the cosmic polar force will correspond to a force which is orthogonal to the surface and can be understood in simple terms as the interaction of the dipole describing the atom with its image dipole. Very simple. So what happens when now the atom is moving? So when the atom is moving, because propagation has a certain time, the image dipole will be delayed. So it's not exactly below the atom, but is displaced backwards. So again, you can see an interaction, you can describe an interaction between the dipole and its image. At this time, the force is not orthogonal to the surface. We will have a component parallel to the surface. And this is quantum friction. Right? On top of that, of course, you have to consider the fact that the atom is not only interacting with its image, but on top, because of the motion, there is some Doppler shift that enters in the calculation. Okay? So quantum friction has been the topic of a lot of work in the past, I would say, 20 years. Yeah, that. And despite this work, there is a lot of problem in finding a coherent description of the phenomenon. I just list here some results that can be found in the literature. I apologize, probably this list is not updated. Just give give quantum friction as a function of two parameters: the velocity of the atom and the distance from the surface. So as you see here, we have several results which describe quantum friction sometimes linear as a force which is linear in the velocity, sometimes non-existing, and other times which is proportional to the third power of the velocity. Same problem here occur when you have the dependency with the distance. You see that the power laws can be rather different. So there was a lot of work. Again, this what is important is that I'm considering, and this is something I should have highlighted at the very beginning, considering zero temperature. So temperature here set to 0. We have only vacuum fluctuations. Recently, we came up with a result. I, Diego Dalve, Intravaia and Union, we published this result in 2014, and we described quantum friction within, we believe, a general statistic theory, and we proved this within this theory that the behavior of quantum friction is proportional to v to the third, and the distance dependence is the distance in the power law that goes with the power 10 to the minus 10. It is important to notice that this value of the exponent here is depending on whether you are describing your moving particle with intrinsic dissipation or with induced dissipation. When I say induced dissipation, I think, for example, to an atom where the atom itself has no dissipation source, but because of the interaction with the electromagnetic field, it acquires a radiative damping, and this radiative damping participated to the frictional process. So this is important because if there is an intrinsic source of dissipation, as for example for a nanoparticle moving above a surface, you will have that the behavior is not t to the minus 10 is t to the minus 7. But the power law will stay. At least this is the result of our theory. And when you have an radiative damping, the power law changes. So I will focus in the follow only on radiative damping. So we'll consider systems like atoms where there is no internal source of dissipation. What is important to know also is that the problem is not only at the level of the functional dependency on the velocity and on the distance of the surface, but there are a lot of differences also among the different factors. And this is a point which is actually not negligible, and I will show you why in a moment. Okay, so let me just give you a very quick overview on how we calculate quantum friction. Okay, in our approach, quantum friction is described as a convolution of two quantities. One is the electromagnetic Green function, describing the geometry we are working with, the surface in this case. And the other is the power spectrum, the dipole power spectrum, which is nothing but the Fourier transform of the dipole correlation tensor. Okay, so the important thing is that in our theory, we are including all non-equilibrium effects. So, and this is highlighted in the fact that the power spectrum is intrinsically depending on the velocity of the particle. Here we are assuming that the particle is moving along the x direction. So if we are able to describe the power spectrum exactly, our theory gives an answer for the frictional force. So for the Green function is generally very easy. For a surface, there are exact formula, analytic formulas. For the power spectrum, it's actually more complicated. And people have tried to have used several methods to calculate. And the fact that several methods have been used with different approximation also explains why there are so many different results in the literature. So one of the most common way of calculating this power spectrum is to rely on something which is called local thermal equilibrium approximation. So this is approximation probably is not the first time that you heard about, because it has been used in several contexts. For example, people working with heat transfer do this all the time. Do you have two bodies at different temperature? What you do, you assume that the first body is local at equilibrium with that temperature, and the same you do for the second body. Why it's important to consider that each of the bodies is a thermal equilibrium? Because if this is true, you can use the fluctuation dissipation theorem. And this fluctuation dissipation theorem establishes a connection between the power spectrum and the polarizability of the atom. Okay? So what you do is that you basically take a box around the atom, take a box around the surface, and you say, okay, here the field is at equilibrium with my body. This approximation is actually interesting and meaningful because somehow it relies most of the time on the fact that the correlation length between within the system is rather short, and the dynamics of the system is fast. So that basically here the equilibration process is occurring very fast, and here too. So basically there is no time that the information goes from this object to the other object. However, what is important is that this approximation has been used only on a phenomenological basis. So a lot of people used it without justifying, saying only that it's reasonable to assume that. However, when we work with quantum friction, things are a bit different. And in general, we believe that this, in reality, for all non-equilibrium phenomena, things are a bit different. Because the real way of describing this system is not where we assume that each of the single bodies is at thermal equilibrium, but because there is an interaction between the surface and the atom. For example, the first kind of interaction is the one that induces dissipation. Radiative damping is depending on the position of the surface, Parcel effect, right? And since we are considering systems within this dissipation with radiative damping, we can already guess that there are some problems in this kind of description. right? So generally, the right way of describing the system is indeed to include the correlation between those two objects, and therefore to consider the full non-equilibrium problem. Okay? In this case, you can no longer use the fluctuation distribution theorem. It doesn't work, right? The problem is not, the system is no longer at equilibrium. So, is this correction small? The correction coming from the interaction and the deviation from the one that from the result you will get from the local term equilibrium case. Okay, so there are several ways of assessing the quality of an approximation. Probably one of the simplest is you take a model that can be solved exactly. And you see if the approximation applied to that model leads to a discrepancy with the correct result. Okay, this is exactly what we have done here. So what we have considered, we have described the atom as basically a simple harmonic oscillator. And we have solved the dynamics coming out of this non-equilibrium case. We are working non-relativistic, so the velocity will be much smaller than the speed of light. If you have, this is the equation describing the dynamics of the dipole in its rest frame. And if you have the stationary solution of this equation, you can calculate the power spectrum using this relation. Okay, what we get? We get that, indeed, the fluctuation distribution theorem is no longer valid. In addition to the term that I showed you before, we have an extra term, which is also known or very similar. The structure of this equation is very similar to something that's been already studied in classical systems. Generally, this term is associated with the current of entropy, right? However, the fact that we have this, if you want, new fluctuation distribution theorem, non-equilibrium fluctuation distribution theorem, tells us that the LT is not working, right? And there is a correction to the frictional force that has been calculated using LT. How big is this correction? Well, surprisingly much larger than what people believed at the very beginning, or what was expected, or what one would expect. And those are the low velocity expansions of those two terms. And as you see here, the prefactors are very much alike, of the same order of magnitude. This quantity ALT or AJ are just a geometrical fact that comes from isotropic sandwich of the atom. However, the prefactor here are very similar. And what is more surprising, the dependency on the parameter of the system is the same. So the correction due to non-equilibrium with respect to the local thermal equilibrium is of the same order than the force predicted by the LT approximation. The other parameters, just to complete the information, is the polarizability, the state polarizability of the particle, and this is the resistivity of the surface. Good. Okay, so we have this result, and then let's plot at least already we know that the correction coming from non-equilibrium is as large as the value predicted from the local thermal equilibrium approximation. So there is a correction which is already almost 100%. And if you need to make a plot of the quantum frictional force, you get this curve, you get this beautiful power law dependence here, and then in this region, you compare the result from the LTE with the full result, and you see here it's not really 100%, but the correction is 80%. Interesting, if you go at higher velocity, there is a region where the power law starts to be valid, and the behavior is exponential. This is a region where the frictional process can be understood from a kind of resonant process between the field and the atom. And in this case, the fact that there is damping inside the particle is not really important. And therefore, the radiative damping can be set to 0. In this case, it's equivalent to consider no interaction between the atom and the surface. Therefore, the local thermal equilibrium approximation is a good approximation. All right. So friction is larger than we initially thought. Okay, let me just switch gear and give you another perspective, another future on see a frictional process from another point of view. To go there, before I have to give you a reminder of another effect that probably all of you know. It's actually rather famous. And the idea is that when you have an atom moving in vacuum, and with a constant acceleration of this atom does not see vacuum as a thermal field, right? This is the Ullrich effect, or is actually has been studied by Stephen Fulland since 1973, and therefore probably the nicest way to call this is the Fulland-Davis effect. So what is interesting is that its temperature is depending on the acceleration of the object, and other constants which are only kinematic. So they are connected only with the Boltzmann constant, the speed of light, and this is the only information about the dynamic of the object. So the question, how do you generally calculate this effect? There are several ways. One of the simplest way is that you just go to use Rindler coordinates, and you evaluate the mean value of the Rindler creation and dilation operators over the Minkowski vacuum. And this turns to have a thermal expression, and the temperature connected with this thermal expression is exactly this quantity. So what is important here is that, as in the case of friction, an external force is needed to keep the atom with constant velocity. So the question is, okay, we have a similarity here. Can we also do apply a similarity at this level? And the answer is yes. So now look at friction, a bit like at the Fully-Davis-Ullrich effect. So you have a force, and can we define temperature for this system? If we require the same kind of constraint that everything depends on the kinematic in the system, by dimensional reason you get the temperature that looks like this. Okay. Can we demonstrate that this temperature is correct, actually? Yes. We use, again, the fluctuation dissipation theorem, but we remember that now this formula does not apply in our case, but instead of this formula, we should use this one, right? This one can be recasted, however, in a configuration which is similar to this one, which is the equilibrium case, and we define, in this way, an effective occupational number. If we have this occupational number, we can calculate it. By just comparing it to the Bose-Einstein occupational number, we can define temperature. This is the temperature that comes out of the problem. And this is defined with respect to some parameters where the GI is the scattering part of the ring tensor. Okay. So we have this expression. Let's do some asymptotics. We look at the behavior of the temperature it's a temperature depending on the frequency, right? This is important. So if the system was thermal, so if the field was felt as it was thermal, this temperature would be constant, exactly as in the case of the Fully-Davis-Ullrich effect. And indeed, if you do some expansion, and analyze this formula at low frequency and at high frequency, you will find that the formula are exactly the same within few percent. So there is a small prefactor here, which is of the order of 3 over pi. Let me give you a visualize this. And make a plot of this effective temperature for different parameters. Here I use different velocity, here different distance from the surface, and here different dissipation in the surface. And I see that, and I normalize this with respect to this high frequency temperature. So as you see here, you go for a value which is exactly 3 over pi to a value that is 1 because of the normalization. So the temperature is constant over the whole range of frequency within few percent. So it's indeed, with a good approximation, a thermal process, or it's a thermal, like thermal-like, let's say this way. There is a bit of some bumps Response depends on are located at the transition where the frequency goes through a characteristic frequency of the system. It's the length scale or a frequency scale of the system. It's given over v over the velocity divided by the distance. And interesting, since the surface, in this case was a metallic surface described by the Drude model, the surface has an excitation, there is also a spike here, which is due to the excitation of the surface. Okay, let me conclude, otherwise the German will kill me. So, what I show you is that within a statistical description of quantum friction, the quantum frictional force at zero temperature is depending on the third power of the velocity. Non-equilibrium physics is relevant in quantum friction. You cannot neglect non-equilibrium, at least in a simple model it shows that the correction coming from non-equilibrium with respect to the local thermal equilibrium approximation is about 80%. So you neglect, you may make a big mistake, at least in that model. In the case, the frictional process can be described in analogy to the Fouling-Davis-Unruh effect as if the particle, now moving with constant velocity and not with constant acceleration, is feeling a field which is thermal-like in nature. And the temperature is actually, the techniques help me, not so low. For an atom moving at the velocity of 314 square meters per second over a surface at a distance of 10 nanometers, reasonable values, the temperature is of the order of 130 millikelvin. So, in reach of, I believe, a lot of experiment with that. Okay, so this was the last point, and I want to thank our knowledge of the funding agents. Thank you very much.
I've got one or two questions. I see one, two.
So Henry has this calculation of two dielectric surfaces, friction, and the effect is linear. What went wrong?
I think that it does not have. Depends on the velocity regime. So
no velocity.
The no velocity, I think, was also power 3.
It's cubic.
It's cubic.
I confirm it's cubic.
It's cubic.
So at the very beginning, you showed again, going in that direction, you showed us this long list of predictions, and you came up with your own prediction. And do you have also an idea why all the others were, let's say, wrong? Because if I have to buy your product, you should.
Yeah, sure, of course, yes. So let me just go there. So there are some problems with some of the description there. Most of the time, it depends on the kind of approximation that you are using to describe your system. In particular, how do you calculate the power spectrum? The power spectrum is a really wild beast, and depending on the approximation that you are using, you can make mistakes. And since this is an integration with frequency, you better describe the power spectrum as good as you can over all the frequency. In some cases, you had obvious mistake. For example, in some of them, in this one, he had some problem. In some other case, they also got a frictional force which was different from zero with perfect reflecting material, which is impossible. It should be zero because of Lorentz invariance. So in some cases, there are really mistakes in the calculation, which are too detailed in order to list. In some other cases, just the way you describe your power spectrum, you make approximation that might not be valid in order to, over the whole range of frequency in order to, and this could cause a problem.
Actually, I have a second question. Quick, very quick. Very quick. You define the effective temperature. The question is, can you use it to do something? Or, for example, if you change it, if you look at another observable, would you get exactly the same effective temperature?
This is exactly a good question. I was actually thinking about that. I don't know. I won't make any claim, but I believe so.
Very quick, very
In the end, we have this sigma zero,
Yes.
which looks very similar to the behavior of the imaginary part of the polarizability at zero frequency.
Okay, so this sigma zero is related with the spontaneous decay of the atom in vacuum.
Because most of other approaches, they produce something which involves integral with imaginary part of the polarizability.
Yeah. So that's absolutely correct. Indeed, when you take the imaginary part of the polarizability, what comes out is the decay rate, right?
Exactly.
And this quantity is related to the spontaneous decaying vector.
And it's also omega cube.
Omega cube.
But it also differs by something with pi in the denominator in comparison to the what the real part of the polarizability goes to, which would be, I guess it can.
Yeah, well, this is indeed related to the imaginary part of the vacuum green tensor, I guess. It's related.
So if Stephen comes up for filling up the next talk,